Okay, today is March 22nd. So I'm going to go ahead and work on some problems from chapter 1 from the ALEKS homework set. So hopefully you're making progress on doing these ALEKS problems for chapter 1. And again, feel free to reach out to me if you have any questions about any of them specifically. So what I'm going to do is I'm going to look at one from chapter 1 again. The topic here is called calculating mass density. Okay, so let me write that down. Calculating mass density. So there's a nice little problem here they give, where they give you some information about some different materials. So what they do is they say there's a chemist working as a safety inspector, finding an unmarked bottle in a lab cabinet. And a note on the door of the cabinet says the cabinet is used to store bottles of methyl acetate, diethylamine, ethanolamine, tetrahydrofuran, and dimethyl sulfoxide. So the chemist plans to try to identify this unknown liquid by measuring the density. So here are the liquids that are being considered. The first one is called methyl acetate. And the density is 0.93. And the way that ALEKS represents the units, it looks something like this: grams dot milliliters to the -1. That's the same as grams divided by milliliters. And those are typical units of density. Mass, grams, divided by milliliter volume, which is in this case milliliters. Okay, so this little glass of water here, that's probably about 100, maybe closer to 200 milliliters. That's about 200 milliliters. Okay, so notice the density of methyl acetate is pretty close to 1. Water has a density of 1. So methyl acetates, actually the density is pretty close to that of water, right? 0.93 compared to 1. So there's one of them. The second one is diethylamine. Now this one has a different density. It's a lot lower. This is a relatively low density. Again, grams dot milliliters to the -1 is grams divided by milliliters. The second one, ethanolamine. This one has a density almost exactly the same as water. Pretty interesting. This is all done, the temperature, actually it doesn't give the temperature in this particular problem. Typically you would give the temperature. I assume it's room temperature. Tetrahydrofuran. And that one is 0.89. So a little lower than water, right? And then finally dimethyl sulfoxide. This one is often called DMSO. You may hear about it in the media. 1.1 grams milliliters -1. Okay, so there are your densities of these liquids. There's 5 potential liquids that the unknown liquid could be. So now they give us some information about the unknown liquid. So what they tell us is that it has a volume of 1623 centimeters cubed. And then they tell us the mass is 1.15 kg. Okay, so here's an issue for this particular problem. If you look at the density values for the materials that they gave you, right, the potential materials, those densities are in different units than the mass units and the volume units they give you for the unknown. See, this liquid has a volume in centimeters cubed and a mass in kilograms, Whereas the density of these liquids that you're interested, the potential candidates for this unknown, those are in grams and milliliters. So it's not as far off as you might think, and here's why. There are different names for the same unit, unfortunately. So one of the most famous examples of different names for the same unit is what's called the cc. The cc is called a cubic centimeter. Okay. If you go to the doctor's office and they measure out a volume to inject you with, it's typically in cc's, 0.5 cc or 5 cc, cubic centimeters. But a cubic centimeter is the same thing as a centimeter cubed. Okay, that's the same thing as a cm3, cm to the third, centimeter cubed, which is the same thing as a milliliter. And so what you'll find is that textbooks and lecturers and workers in the fields will use these three names interchangeably. So a milliliter is the same thing as a centimeter cubed. So even though this says centimeter cubed, we can also write it as milliliters, and that's very helpful, okay? I won't go through the derivation of that. I could do a mathematical derivation to show you that they're identical units, but it's not worth the time for us right here, okay? So 1623 is the milliliter, so that gives us the same units we have over here, right? Now the other issue is that the mass is in kilograms and densities, the way we're reporting densities in this table is in grams. So we have to deal with that. So here's what I'm going to do. I'm going to remind ourselves that there are certain prefixes, which I did in the previous lecture. And one of them was the kilo. And the kilo has an abbreviation K, lowercase k, and it means 1,000 or 10 to the third. 1,000 is the same thing as 10 to the third, 10 times 10 times 10, right? So here's what I'm going to do. I'm going to convert this mass in kilograms into grams. And that way it'll be the same units as our density over here. So let's take our 1.15 kilograms, and I'm going to do a conversion. Now, here's how I'm going to do it. I'm going to write it out that 1 kg, 1 kilogram. Remember, you got a number, a prefix, and a unit. That would be equal to 1,000, because a kilo is 1,000, and then grams, right? So here's the number without a prefix, right? That's what we're doing here, is we're getting rid of the prefix, and then there's our unit. So number, prefix, unit, or number, unit. Now we write this as an identity. So what we do is we say, look, 1,000 grams over a kilogram. We have it in kilograms. We want to get it into grams. So I'm going to put this one on the top, and the one we're getting rid of, I'm going to put this one on the bottom. We're getting rid of the kilograms. Okay, so let's multiply it by that ratio. So times 1,000 grams over a kilogram. And so you get 1150 grams. I'll put the decimal point there. So there's our mass. And now we have both units for density. Density is mass over volume, pretty straightforward. So I'll work that up over here. Density is mass over volume. Oops, let me be careful here. Or m over v. It can be written as m over v. And so our mass is 1150 grams. And our volume was the 1623 milliliters, right? Centimeters cubed is the same as milliliters. So now if you look at those two numbers and you do the division, mass over volume, you're going to get a number that's around 0.7, it looks like. So let's run that through. 1150 divided by 1623 It's about 0.7. It's 0.0. I tend to put the 0 before the decimal point. 70856. I'm going to round it right there to 4 sig figs. We'll talk more about sig figs. Can anyone hear me? Yeah, actually, can you put it in the chat? Can anybody hear me? I don't want to get in a situation where no one. Okay, good. All right. So what I would recommend, Nacha, is you just go ahead and check to make sure that your volume's up. And then if it doesn't work, maybe try to disconnect and reconnect. Okay. I did have some problems with this computer this weekend with sound, so hopefully that's not the issue. So 0.7086 grams per milliliter. Okay. Now all I'm going to do is I'm going to just come over here and look at which one's closest to that value, right? Like if you measure something and, it's closest to that one, that's the one we would assume it is. So it looks like this is the one that's closest, right? The dimethylamine. Okay, or diethylamine, I'm sorry, diethylamine. Diethylamine says it's 0.71. Well, 0.7086, that's really close to 0.71. It's pretty far away from 0.89. It's pretty far away from 1.1. It's pretty far from 1.0. It's pretty far from 0.93. So it must be the diethylamine. It's got to be that one. Okay. So the answer would be it's diethylamine. Now, when you do these ALEKS problems, they probably should tell you how many significant digits to report the answer to. So in this particular problem, they say report your answer to 3 significant digits. Okay. So here's what you would do for this particular one. You may notice that I wrote 4 numbers here. Those are called digits. Those are called significant digits. If the question says report it to 3, what you do is you start on the left side. Let me write the number down here. Oh, by the way, we could also write this as grams times milliliters to the -1. That could also be written that way. Okay. So this you start on the left. So you start on the left side and you move to the right. So the first one is a 7. That would be the first significant digit. The 0 would be the second. So that's 2. The 8 would be 3. That's the third digit. So it says report to 3. So that means we're going to stop right at the 8. Now, what you do is you do rounding. If you remember how to do rounding, if the number coming after your last digit that you want, so the 8's the last digit that we want, the number after that, if it's 5 or greater, you round the 8 up. So since 6 is 5 or greater, you round up and you get 0.709. Okay, so the answer for this one would be 0.709. So when you're running these problems through your calculator, feel free in this step right here to report lots of sig figs. You could put 4, you could put 5. Generally, what I do is I look at the question. If it says it wants 3, I keep 1 extra. And then I round it when it says to put the answer in. So there's a little box in this question, calculating mass density, where they ask you to write the actual density to 3 sig figs, significant figures. So that's where I would do the rounding. So 1, 2, 3. If they had said, rounded to 4 significant digits, and actually you could justify doing that with this problem because they gave us good enough numbers that we could do 4. If we were going to report it to 4, we would just write 0.7086, and that would be 4 significant digits. If they wanted it to 2 significant digits, so notice this one only has 2, and this one only has 2. Actually, they all only have 2. These all only have 2. So if there's only 2, if they only want 2, then what you would do is you take your 709, and your second one would be right here, and you would round that up to a 10, right? So it'd be 0.71. So 2 sig figs would be 7.1, which, that's the same as diethylamine. So whoever did this experiment did a really good job. They measured the mass and the volume very precisely, very well, or very accurately. So now, they got the 0.71 to show us that it was diethylamine. Had they gotten 0.92, then you would say, oh, it's closest to methyl acetate. So this unknown liquid must be methyl acetate, and likewise with any of the others, okay? So that's called calculating mass density. That one's I wouldn't say it's a lengthy problem, but there's a couple of steps in there that you have to think about, okay? Let me see, so that's density. There's another density problem, which I think is worth kind of looking at. So let me create a new board here. And it's called using mass density to find mass or volume. So when you do these ALEKS problems for this particular problem, sometimes they're going to give you the density and they're going to give you the mass and they want you to find the volume. Other times they're going to give you the density and they're going to give you the volume and they're going to want you to find the mass, okay? So I'm just going to write our definition of density here. Remember, density is mass, M, over volume, V, right? It's a ratio, right? A density is really two things together. It's the mass of something divided by the volume that it's taking up, okay? And so we all recognize that if something is in water and it's less dense than water, like a piece of wood, it will float, it has buoyancy. If it's more dense than water, it doesn't have any buoyancy and it will fall down to the bottom of the water. Liquids will do the same thing. If you mix liquids together and they're not really good at mixing, the more dense liquid will go down to the bottom and the less dense liquid will go up to the top. So that also works with liquid mixtures, okay? So let's take a look at this problem. It says that a chemistry student needs 45.0 milliliters of chloroform, okay, for an experiment. And by consulting the CRC Handbook of Chemistry and Physics, that's a kind of famous book that people use to look up values, the student discovers that the density is 1.48 grams dot centimeters cubed. Calculate the mass of the chloroform. Okay. Calculate the mass of the chloroform here. Okay, so here's what I'm going to do. I'm going to sort of just look at the information they gave me. They gave me this piece of information right here. That's volume, right? Okay, so let me remind you, volume has many different units. Remember, volume is just the space. So like think of a cup. There's a certain amount of space of this liquid. Typically the problems you do, you're talking about the density of a liquid, but not always. Volume, the units are milliliters. And remember, a milliliter is the same thing as a centimeter cubed. That's the same thing as a cc, cubic centimeter. There's also just liters. This is just called a liter. And so when you buy, these days, the metric system has kind of made its way slowly over time into the United States. If you're from another part of the world, you're more familiar with it. But milliliters and liters are very common units of volume. A milliliter is 1/1000th of a liter, or another way of putting it is a liter is 1,000 milliliters, okay? Those are the most common units that we use in chemistry. Physicists will often use meters cubed. This is called a meters cubed or a meter cubed. Okay, just like cm to the third is centimeter cubed. So chemists tend to use these units here, and then physicists tend to use these units here. Okay, so we know the volume, 45.0 milliliters. So we've got our volume. It also gives us the density, right? So we have our density. So the only thing left to do is to find the mass, right? So really this problem Be careful when you do it because there may be some unit conversion. You may need to convert, meters cubed to centimeter cubed or kilograms to grams or what have you. But typically, it's a relatively simple problem. So I'm just going to go back to it real quick and just make sure. Calculate the mass of, okay, so it just says the mass. It doesn't say what units to put in, okay? So if it doesn't say what units to put the mass in, just assume it's the same units they gave you here, right? If that's in grams per centimeter cubed, so this is -3, sorry. -3, because it's divided by centimeters cubed, right? Okay, so since that's in grams, we would assume our mass is in grams. So let's go over the basic algebra here. D equals m over v. We want to know m. So the logic of this would be that we want to isolate this mass. So anything that's with the mass needs to be on the other side, right? So I'm going to multiply both sides by volume. If you multiply the right side of the equation by volume, you now have, see how we could write this? I apologize if this seems too simple for you, but what you really have is mass times volume over volume, right? Volume over volume, and that's 1, right? That's the same as 1. So you just have mass on the right side. And then on the left side, you have volume times density. Okay, so there's your algebra. So now we can just, it looks like our units are okay because, again, a milliliter is the same thing as a centimeter cubed. So it should be okay. So just to make it clear, what I'm going to do is I'm going to write this as 1.48 grams dot milliliters to the -1, right? Milliliters a centimeter cubed. So now we can go ahead and use that. So volume is 45.0 ml, right? So there's your volume. And then our density is 1.48 grams. Okay, so now I find it more, more useful to write it, just in terms of how you write the units, to write it this way. It's fine if you want to write G times ml to the -1, but for me, it's helpful to write it this way because then you can see how they cancel, right? Because that ratio is 1. So V times D, our units are going to be grams, and that's going to be our m. And that's what you're expecting, right? Mass should be like either grams or kilograms or centigrams or milligrams or micrograms. Volume should be milliliters or centimeters cubed or cc's or liters. So it looks pretty good. So 45.0 times 1.48, and you get 66.6. And then again, our units are here. That's our mass. Okay, 66.6. All right. And yeah, that looks pretty good. Let me take a look and let's just confirm how many sig figs. It says round your answer to 3 significant digits, right? So 3 significant digits. Okay, well, we already have 3, right? If you put the numbers in that they give you, the calculator gives you an exact number. 66.6 actually like an exact calculation here. There's no rounding or involved. So we've already got 3 significant digits. So we're done with that one. Okay. Again, with these problems, they may ask you to find the volume. They'll give you the mass and they'll give you the density, and then you find the volume. But it's essentially the same type of problem. You would just solve for volume. Okay. Okay, so that is actually section 1.3, scientific measurement. And then you've got this section 1.4 called the properties of matter. And I do want to talk a little bit about one of these because they do kind of go into detail in this homework set about the language of properties of materials. And so there's a lot of language that's used here. So I want to talk a little bit about it. Okay. So the one that I'm looking at here is called distinguishing physical and chemical properties by a macroscopic description. Macroscopic means big picture, like something you see with your eyes. So they're going to give you a description of the macro, like for example, this material here is a liquid at room temperature, and it is fairly viscous, meaning that it flows relatively slowly if you try to slosh it around. It seems to have bubbles dissolved in it. That's a macroscopic description of water, right? Okay. So in this particular problem, they say they do some experiments, and then there's some description of the experiment. In each case, decide whether the property measured was a chemical or a physical property of X, X being the material, if you can. If you don't have enough information to decide, choose can't decide in the third column. Okay, so they're going to give you a property, and then they're going to give you an experiment, and then they're going to ask you, is this a physical property or is it a chemical? And you just have to decide. And there's three options. You can either be physical, chemical, or can't decide. So in the first one, a sample of X is melted. Okay, so when you say something is melted, that means it started off as a solid, and then it got converted into a liquid, right? That's what melting is when you take something that's a solid and you make it a liquid by heating it, right? You put it into a reservoir from which a very thin tube leads down, okay? So you've got this reservoir and you have a little thin tube that leads down, okay? And the rate at which X flows out of the tube is measured, and from this rate, the value of V, which is the volume, may be calculated. Okay. So in other words, what they're doing is they're melting a liquid. Okay. So the property that they're looking at is what we would call the melting point. And they're measuring its volume. Okay. So when we talk about chemical properties are properties that involve a rearrangement of atoms. So for example, if you strike a match, the material on the head of the match is being converted into something else. It smells, it's a gas, it's a completely different material. That's a chemical property. Rusting, if something is changing from steel or iron into iron oxide or rust, that's a chemical property. Digesting food's actually two properties. One is you're just sort of mixing the stuff together and kind of breaking it up physically, right? That's physical process, physical property. But there's also the aspect that the molecules are being broken down by enzymes. That's a chemical process. So when you read through these, be careful what they're looking at. Typically, if they're saying, hey, the volume changes, the temperature changes, that's typically a physical property. So melting point is that's a physical property, because they're talking about how the material is changing physically. It's changing from a solid into a liquid. That's melting. That's a physical process. So melting, boiling, those are physical processes. So let's take a look at the second one. The second one says this sample, so we can say right there, this is physical. The second one says you've got a sample, it's carefully weighed, put inside a vented flask. Okay, so you got this flat, that's a flask. It's essentially a container, like a jar. Vented just means that if there's any gases, they can escape. That's all that means when you say vented. Okay. Water is added to the flask until it covers the sample. Okay, so they don't really tell you what the sample is. They just say there's some sample in there, and then they cover it in water. Okay. Till it just covers the sample. Okay, so let's do this. The water just barely covers the sample. The volume of the sample and the water is recorded. Then the sample is removed and the volume of the water alone is recorded. From the mass of the sample and the differences in volumes, the value of R may be calculated. Okay. So be honest with you, I don't know where the R is coming from. I don't know why they picked that symbol in here. But essentially, here's what they're doing. They're saying, look, you've got this container. There's a sample in there. They don't tell you whether it's a liquid or a solid. I would assume it's a solid because you don't generally cover a liquid with another liquid. You mix a liquid with a liquid. But if you had a rock, you could cover it with water. So then they say they weigh it. They find the mass. And then they say that they pour out the water. Okay. And then they weigh it again. And then they take the difference between the masses. We'll call this M2 and we'll call this M1. So they take the difference, M2 minus M1. The reason you would do that is that that would be a way to determine what the mass of the rock is, or the mass of the sample. Okay, there's your sample. Okay, so really all they're doing is they're measuring density. They're measuring the density of this material. They're figuring out what the mass is. They're figuring out what the volume is. They're figuring out the density. Density is not a chemical property. So even though different chemicals have different densities, it's really a physical property. It's really just how much mass something has divided by how much volume it has. So how much does it weigh? That's a physical property. How much space does it take up? That's a physical property. That's not a chemical property, okay? Again, a chemical property is a reaction. And although you don't know all the reactions in nature, you know a lot of them. Striking a match, flicking a lighter, turning on the burner in your kitchen, exhaling carbon dioxide from your body that's done all these chemical reactions. Burning stuff is typically chemical reaction, right? Well, it is. So this one's, again, it's also physical. Okay, it's density. You're just trying to figure out what the density, color, temperature, boiling point, melting point, these are all physical properties. Okay, they're not chemical. And then the last one, the third one here, is they say, okay, well, let me make a little space here. In this one, they say you've got a solid X. So now they tell you it's a solid. And they carefully weigh it and put it inside a sealed flask. So sealed flask means that they have a cover, like a cork. So you got a cover there. And then there's a solid. There's your X. They weigh it, they put it inside the flask. Pure hydrogen is added. Now that might be a sign that there's going to be some kind of chemical process because they're telling you what element they're putting in there. Hydrogen is put in there and starts, a mixture is heated until the hydrogen starts getting consumed. So they're going to heat it. So the way I'm going to represent that is with a little burner. It's called a Bunsen burner. Okay, so they're going to heat. There's heat. Okay, then here's what it says. It says the hydrogen gets consumed. Consumed is a key word in chemistry. Consumed typically means a chemical reaction. Okay. Produced or consumed or used, typically a chemical term, okay? Really what they're saying, okay, let me read it to you again. After hydrogen stops being consumed, the contents of the flask are removed and weighed, and from the increase in weight, the value of may, I think what they mean is the value of Q may be calculated, okay? So here's what's happening. They're heating it, The hydrogen is adding to the sample. There's a reaction taking place. The weight changed. So be careful, even though it talked about weight, which is a physical property, the language in here about something getting consumed, the hydrogen getting consumed, that's telling you a reaction is occurring there, okay? So this would be a chemical process. All right, so, you know, this particular problem is really a lot of reading and then kind of interpreting what's happening. And that may be a little challenging for you because you're not in a laboratory. If you were in a laboratory and you were watching this happen, you'd be able to say, oh yeah, I can see there's a chemical reaction, right? Like when you see things bubbling, when you see light coming off of something, when you feel heat coming off of something, yeah, that's a chemical reaction. But typically, if you have to heat something and then you see something getting consumed, not that you could see hydrogen get consumed. You actually can't see hydrogen gets consumed, but they somehow said you could. That would be telling you that there's a chemical reaction occurring, okay? You can also use your intuition in this. Like if you're reading through it and it talks about a match, you know that's a chemical reaction, okay? So that's the sort of intro, in a sense, to physical and chemical properties, okay? Let's see here. Distinguishing chemical and physical change. So there's another problem in here where they give you some pictures, and you may not be used to doing that as well. So this one is called distinguishing chemical and physical change. Okay, so there's 4 sketches. So they give you 4 little drawings. In the first drawing, they show you something that looks like this. Oops, let me redraw that. Okay, those are 4 atoms bound together. They don't tell you what the substance is, but those are 4 separate atoms that are bound together, and they give you a bunch of them, okay? So I'm only gonna draw a few of them, but they draw like 10. So these are molecules, 4 atoms across. The 2 atoms on the ends are different from the atoms in the middle. So that means there's 2 elements. So it could be, for example, nitrogen in the middle and oxygen on the outside. You don't have enough information to tell that though, but that's okay. So then they show you 3 outcomes, okay? And the first one on the left, which they call change 1, what they show you are a rearrangement of the atoms. Okay, I'm not going to draw a bunch of them. I'm just going to draw one there because they're all the same in that picture. And they want you to determine whether this is chemical change, physical change, or impossible, which is an interesting option, right? Okay, let's look at the second one. The second one, what they do is they change the color. So they take these atoms that are in the middle, the darker ones here, and then they use, here, let me see if I can switch the color. They actually have a different color here now. So now they got something else. Oops. Okay, so let me go back to the regular color. Okay, so there's your second option. And then the third option is 6 of these, colored in. I colored them in, I shaded them in the middle, and then 6 of the open circles. Oops. Okay. All right, 1, 2, 3, 4, 5, 6. Okay, cool. I actually like this problem. I hope you enjoy this one because it's really it's kind of fun. This is like one of the things I really enjoy about chemistry, which is you're actually like seeing like how things are structured. Okay, so here's the notation that we're using. When we draw pictures like this, if you see something like that, that's an atom and it's an element. So I'm just going to say it's carbon. Now, have no real, only a little bit of anecdotal evidence that it's carbon. But my point is that anywhere where you see one of those little discs, those little balls that's shaded in, that's a carbon, right? So each of these are carbon. Right, that one too. And those ones in the middle there, those are carbon, okay? And then there's another element on this different. It's different, right? It looks different. It's not shaded in there. So that's a different, it's an atom, but it's a different element, right? It looks different. And that's how we think of chemistry, is these atoms. And so I'm going to claim it's hydrogen. In fact, I think it is hydrogen now that I think about it. Okay, it's probably carbon and hydrogen. This is probably what we call acetylene, C2H2. Okay, so there's two atoms in the middle. So I'm just for our purposes, you don't need to know this for this problem, but suppose I said that that was carbon, we would say there's two carbons in there, two of them, right? And then there's two hydrogens, so it's really C2H2. Okay, now let's look at the option on the left, change one. What it has is two carbons, or two of those atoms, surrounded by four of these atoms, right? That's a chemical change. That's really fundamentally what a chemical change is we have changed how the atoms are related to each other. In this case up here, they're related by having two of those carbons in the center and then one hydrogen on either end, right? That's what that molecule is. Down here, now there are two carbon atoms bonded together, just like they were before. But now there's four hydrogen atoms attached to the whole thing. The whole unit now has four hydrogen atoms. So we could write that actually as like C2H4. There's four hydrogens. That is chemically different. So even if you don't know it's carbon and hydrogen, even if you said it's atom A and atom B, that would be a chemical formula, A2B2. Over here, it would be A2B4. That's a chemical change. Anytime the formula changes, that's a chemical change. So by looking at that picture, you can see that that's a chemical change, okay? The second one, that's impossible because take a look at what happened. We now have a different atom. This is a different atom. This is a third element, right? It could be nitrogen, for example, or it could be, you know, any other element. That's impossible. That's not a chemical change. It's not a physical change. That's actually what we would call transmutation, which could, in theory, it could be done in a nuclear accelerator, but even that probably is unlikely that that could happen. So this is impossible. That can't happen. We can't transmute one element, carbon into nitrogen. That doesn't work. That's not going to happen here. So that's an impossible process. So anytime you change the element from one element to another, if it wasn't already in there, like if it was in there and it just got mixed together, then that could happen. But if it didn't exist in the container at all, and now suddenly it appears, that's impossible, okay? The third one, that's possible. If you take a look, again, you have the same elements. You have this one right here, which, again, if you want to call it carbon or you want to call it A, I'll call it A. There's 6 of them. It's a little ring. And you still have this other element, B, and there's 6 of them. It's really C6H6, which is called benzene. So it kind of took me a while to figure this out. But that's really what it is, it's benzene. This is a chemical change. Okay, so you might ask, what would be a physical change then? Like 2 of them are chemical, one's impossible. What would be a physical? Here would be an example of a physical. If suddenly these things reappeared down at the bottom And now they're like this. Okay, see how I'm drawing them? This is called a solid. Whereas here, they could be a liquid. Remember, liquids are like this, right? They're less ordered. They can bounce around and stuff like that, so they're not that ordered. But a solid, all the atoms are rigidly held together, right? So this could be, for example, this could be a liquid, and this could be a solid. So remember, solid to liquid, right? So if they undergo that change from a liquid to solid, that would be a physical change, okay? So two of these were chemical, one was impossible, but you could also have a physical, and that would just be that either they're really close to each other and now they're far apart, or it could be that they're kind of randomly distributed. One's pointing this way, one's pointing, but now later on, they're all pointing the same direction. That would be physical as well, okay? So that's kind of cool. I like that problem. I hope you do too, but I thought it was kind of interesting. Okay. So once you finish that section, that's section 1.4. The next section is called uncertainty and measurement. Okay. Uncertainty and measurement has, it looks like it's about 5 different types of problems, and these are getting back to numbers, okay? So let me, some of this is going to be really review for you because it's stuff that you did back in high school or even before then. But let me at least go over 1 or 2 of them. So the first one is called rounding, because sometimes people forget how to round, right? You learned at some point, but we are pretty unforgiving when it comes to stuff like this in the sciences, in the physical sciences. So let me go over this one. Okay. So here's what they do. In this question, they say a chemist needs to know the mass of a sample of sodium sulfate to 2 significant digits. She puts the sample on a digital scale, and this is what the scale shows. I guess one thing I like about this problem is they actually show you like a little digital readout. That's kind of cool. It's sort of visually interesting, as opposed to just showing you a number on the paper. Okay. So in the laboratory, this is what you would see. You'd measure something, and then it's in G. Okay. So all they're doing is they're saying, look, round this to 2 significant digits, right? So we talked a little bit about rounding a little earlier. Oops. Let me stop this share here. Oops, I'm sorry. Okay. It was a little bit of a technical glitch there. For some reason, the iPad wasn't giving the information. So let me write this again. Okay, again, this is called rounding to a given significant digit. Okay, so they give you these numbers, 0.0048.6 grams, and they want you to round it to 2 significant digits. Okay. All right, so again, it's relatively straightforward. Oops. Okay, the reason the zeros are in the front is that, you know, that's what the analytical balance, that's what the machine would show you. It wouldn't get rid of the zeros in the front. It would just write the zeros in the front and show it to you. Okay, so we want 2. So you start on the left side and you go to the right. So this one is what we call the most significant digit. So that one's going to be there for sure. The issue is the ones on the right. How many do you have on the right side? So this is your first one. And then this is your second digit right here. Okay, that's the third digit right there, but we only want it to 2. So here's what you do. You round it to the second, and you look at the number that comes after. If it's 5 or greater, you round up. If it's below 5, you get rid of it. You just lose it. So this is 5 or higher, so you round up. So this you round up. So now you get 49, right? And then just be careful on ALEKS, they want you to show the decimal point when you put in your numbers. Yeah. So just write 49 point units or grams, okay? And then you don't need to write these zeros on the left side. If you're reporting the number, you don't have to write the zeros. The machine would show the zeros, but you don't have to show the zeros yourself. We just wouldn't do that, okay? So that would be 2 significant digits, okay? I want to just show one more. Let's see if there's one that's any a little trickier. Sometimes they'll throw one that's trickier in here. That one's not any trickier. Most of them look pretty straightforward. Oh, here's one. So this one's kind of cool. So in this one, they say a chemist needs to know the mass of a sample of magnesium chloride to 5 significant digits. And then they give you these numbers, 0063.29 grams. Okay. Okay, well, if you look at it, the zeros in the front are not counted when it comes to significant digits. You ignore the ones on the left. These are called leading zeros. And leading zeros are never counted as significant. Okay, just remember that. If they're on the left side of the numbers 1 through 9, so 63.29, those are numbers between 1 and 9, the ones on the left are never counted. You just ignore them, okay? So we start here, 6. That's your, in the tens column, right? That's the most significant. So that's 1. Then you get to the ones column, that's 2. Then you get to the tenths column, the point something column. That's 3. That would actually be the deci column. And then the next one, two columns past the decimal point, that'd be your 4th. That's 4. We're stuck. That's the most we have here. This is 4 significant digits. You can't create more significant digits than you have in the number. So like if someone weighs it with 4 significant digits and they give you 4, so like suppose you said, hey, go to the lab, measure it out, and they came back with 4 numbers and you wanted to have 5, you can't have 5. They would have to get 5 out of the machine. So you can't create out of nothing. So we're stuck here. So here we would have to say you can't get 5. You can always round down to fewer, right? Like, so if I said I want this to have 3, you could round it. You would just say 63.29. There's our 3rd one right there. 1, 2, 3. This one's 5 or greater, so you round up and you get 63.3. You could do that. You could say I could have 2. You'd say, oh, 63.3. This is your 2nd one right here. This is less than 5, so you'd round it to 63. So you could do that. You could get it down to 1. The way you would do that is you say, okay, here's 1. This one's less than 5, so it just becomes 60, and that would be 1. So you can always round down in terms of significant figures, but you can't round up. You can't create more significant digits than you started off with, okay? So if you see one where they give you not as many as they ask for, then you just say, look, you just can't do that, okay? ALEKS will do that sometimes. They'll give you problems where they'll give you the option of, is this possible? Okay. Okay. And then let's take a look. Maybe we've got time for one more here. We got about 5 minutes. Counting significant digits when measurements are added or subtracted. Okay, this is an important one, and it's one that's often overlooked by students. And I usually put this problem off until after I do multiplication division, but I'm going to do this one first because I think it sometimes is more confusing for students than the multiplication division one. Okay, so there's one right there. The second one is, let me just make sure I got this, plus 7.627 ml equals ml. And here they're not telling you how many significant digits to give your answer. You figure this out yourself. That's a minus, by the way. Okay. Awesome. Okay, let me come back over here. Okay, good. All right, so here's how you do addition, subtraction. What you do is you look for the decimal point. So I'm going to kind of put the decimal point really obvious in these numbers. That's the key, is where's the decimal point. You then count how many digits past the decimal point you go for each number. So you see how the first one, 10.58, goes 2 digits past the decimal point? So we're not counting all the significant digits. This number has 4, 1058, but we're only counting the number past the decimal point, okay? The second one, it has 3 digits. 1, 2, 3. Unlike 0 in the front, where you ignore it, if it's on the right, you don't ignore it. If it's to the right of the decimal point, do not ignore it. Okay, so this one has 3. Then what you do is just use your calculator or use your arithmetic in your head if you're like really good in math, and just add it up. 10.58 plus 5.620. And you get 16.200. Okay? Now that's not the answer. And I want to show you how you get the right answer. This is you have to be very careful about this. This is what you do. See how this one only went 2 digits past the decimal point and this one went 3? You pick the number that has the least number past the decimal point. This one only has 2, this one has 3. So if this one has 2, you round your answer to 2. Why 2? Because this one only goes 2. So you're picking the number that has the fewer digits past the decimal point. And then you round your answer to that number. So what I've done, just without really looking at it, is I put it to 3 digits past the decimal point, which is incorrect because this one only goes out 2. So your answer only goes out 2. So how do you fix that? You just get rid of the last 0. Just get rid of the last 0. Right? So now it goes out 2 digits past the decimal point, just like this one here. Okay? Let's try the second one. First step, just add them or subtract them just like you normally would. So 13.7 plus 7.627. You get 21.327. This is volume milliliters, okay? Now you count your digits. 1, right? This, again, when you're doing addition subtraction, don't count all the digits, just count the digits past the decimal point, to the right of the decimal point, 1. This one goes 3 digits past the decimal point. You round your answer to the smaller number. If this one only goes 1 digit, you round it to 1. So then you come back over here and you say, okay, here's the decimal point, 1. So you're going to stop at the 3. Now you do your rounding. The number that comes after the 3 is a 2. That's smaller than 5. So you just truncate it. You just get rid of it, right? If it was 5 or greater, you would round up. So it's not. It's smaller than 5. So 21.3. That would be your answer right there. 1 digit. And then you check. You go say, hey, look, 1 digit, 3 digit. Oh, yeah, it should be 1 digit past the decimal point. I did that. That's right. Okay. Last one. This one goes 1, 2, 3. This one goes 1, 2. So our answer is just going to be point something something. 2 digits past the decimal point, right? Okay. Now this is subtraction. So you go 18.600 minus 13.57. So I'm going to go 5. Now this one, it worked out. My calculator actually just put 5.03 because, you know, it's just what it did. But we know that that's correct because it's only going out 2 digits past the decimal point, and that's what this number does right here, 2 digits past the decimal point, okay? And there you go. So our answer would be 5.03, 2 digits past decimal point. So again, addition and subtraction, you locate the decimal point, measure or determine how many digits past the decimal point the number has. So let's say this one has 4, it goes four digits past, this one goes 2. Your answer is just going to be 2. It's going to have 2 digits past the decimal point. So, add them or subtract them just like you would, but then round them to 2 significant digits. Okay, and there you go. Now, we're out of time, and that was that was counting significant digits when measurements are given for addition and subtraction. So there's one more section in chapter 1, which is called using units and solving problems. And I do want to go over a couple of those because those are important problems. So here's what I'm going to do. Today is the 22nd. But guess what? Next week is spring break. Okay. So here's what I'm going to do. I'm going to go ahead and give a lecture next Monday at the regular time at 9 a.m. And just like always, you're free to be there if you want. But if you don't want to, you don't have to be. And I'm going to post it to YouTube. So I'm going to do an hour lecture on section, the end of 1.5, a little bit more of the significant digits, and then 1.6, which is doing calculations. Those are important problems. Those are really get to the core of chemistry of what we do in Chem 1100 and 1200. So I don't want to just kind of ignore those. And you do have an ALEKS assignment due, I think it's April 2nd or April 4th. It's like the first week of April or something like that. So I do want to kind of keep giving you the information to help you do these ALEKS problems. But again, it's optional if you want to come in on next Monday, but I will do it and I will post it and it'll be up by, 11, it'll be up by 12 on Monday. Okay. So if I don't hear back from you, I don't see you next week, have a great spring break. If you do have questions about any of these ALEKS problems though, reach out to me this week, text me, WhatsApp, Signal, Telegram, whatever you want. And then this particular recording will be up today relatively quickly, and then you can practice on these. So I try to put some effort in this week, right? Because it is spring break and you're gonna have a tendency not to want to work probably during that. So try to get as many of these problems as you can this week, because first week of April, it starts you got your first assignment due and your first test. Okay. So have a great day and have a great week. And I hope everything goes well for all your classes and everything. Take care.